We'll be using a couple of different groups and rings this semester. One of the most important groups is the symmetric group. So we write Sn for the nth symmetric group. This is generated by n-1 generators, S1 through Sn-1, that is little s1 through little sn-1, as opposed to big Sn, which is the name of the group, with relations any generator squared is the identity, Si Sj Si equals Sj Si Sj if I and j are exactly 1 apart and Si and Sj commute. That is, you can write them in either order if the difference in indices is at least 2. So a typical element of the symmetric group is some product of these generators, say Si1 through Sik. And this will possibly have single generators appearing more than once. Then we have pictures that correspond to the generators. So the picture corresponding to S1 is going to have an X and a horizontal line and a bunch more horizontal lines. The picture corresponding to S2 has the same number of horizontal lines and one X, but the X is raised a little bit. So we can think of n endpoints on the left and n endpoints on the right. So here the X occurs between levels 2 and 3 as opposed to 2 and 1. And then Sn-1 has the X all the way at the top and horizontal lines everywhere else. So n-2 horizontal lines, then n-1 and n are where the X is. Now these pictures can help. Excuse me. Let me draw one more picture here for the identity element. So the identity element E we can associate to the picture that has just n horizontal bars. Now the generators can help us multiply and remember the relations here. So the first relation says any generator squared is the identity. So we should think of that as we're going to multiply by concatenating. So if this is any generator and we glue together the pictures, then we can see that the wire going from starting at I goes up to level I plus 1 and then comes back down to level I. So we've got a wire going from 1 to 1, 2 to 2, and whenever there's an intersection, we think of the wire as going straight through the intersection, not turning at all. So we have 1 going to 1, 2 going to 2, I going to I plus 1 going to I plus 1, N going to N. And in this identity wiring diagram, we have, of course, 1 going to 1, 2 going to 2, etc., N going to N. So having these two-line notations for the elements of the symmetric group be equal is the definition of equivalence of wiring diagrams. So we can see that one wiring diagram placed next to itself is just like having the ordinary identity horizontal line wiring diagram. So let's look at the second relation here called the braid relation. I'll try and do that in this space here. So maybe it'll be easier if I do it in S4. So we should have something like S2, S3, S2 equals S3, S2, S3, because these indices are exactly 1 apart. So here's S2, here's S3, here's S2, and then 3, 2, 3 looks like that. So if we follow the wires across, hopefully we'll get the same thing both times. So here we've got a wire from 1 to 1, and a wire from 2 to 4, and a wire from 3 to 3, and then a wire from 4 to 2. Here we have a wire from 1 to 1, and then from 2 to 4, and from 3 to 3, and from 4 to 2. So indeed those are the same. So let's look at this relation now, the commuting relation. So we can do an example in S4 again, I think will be clearest. Now the only two indices that are far enough apart in S4 to serve as an example are little s1 and little s3. So we should be able to see that little s1, little s3 equals little s3, little s1. When pictures, this is, here's s1 and here's s3. And then if we do S3 first and S1 last, we get that. And we can see that both pictures, that is both wiring diagrams, give us 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. And that's because the x's are far enough apart that they don't touch each other, so we can imagine sliding them back and forth, and they're defining the same arrangement of wires. Here's another way of looking at the braid relation. I put some wires up here, some actual cables here on the whiteboard. So we've got one wire going from position, let's say I to I plus 2. We have I plus 1, I plus 2, I plus 1, I plus 2. So we've got the black wires going from I to I plus 2 and I plus 2 to I, and then this black and white wire going from I plus 1 to I plus 1. And if I hold the wire down here so it crosses this wire here and that wire there, we've got an SI followed by an SI plus 1 followed by an SI. And if I lift this up, then we have an SI plus 1 followed by an SI followed by an SI plus 1. So this relation is just saying that if you move this middle wire down a little bit past that intersection or up past that intersection, it doesn't make a difference where the wires are going to end up on the other side. So the notation I've been writing is called two-line notation, where we have 1 through n on the top, and 1 through n on the bottom in some other order. So here we've got I going to I plus 2, I plus 1 going to I plus 1, and then I plus 2 going to I, and then everything else going to itself. So this is called the two-line notation. This has the form 1 through n on top, and then some rearrangement of 1 through n on the bottom. The bottom word, just W1 through Wn, is called the one-line notation of the element of Sn. So two-line notation comes from the wiring diagram, following each wire from left to right and explaining where it starts and where it ends. And one-line notation is just erasing the top word 1 through n and remembering the bottom word. Now, direct connection between the generators and the one-line notation that doesn't use the wiring diagrams treats the generators as functions. So to convert directly from generators, some expression like this, to one-line notation, let's let SI be the function on n-letter words that sends A1 through AN to the same word with AI and AI plus 1 swapped. So that is SI swaps whatever letters are in positions I and I plus 1 of a word. All right, I got rid of the wires. So that means that the one-line notation of S1, S2, S1, S3 is, so we'll apply that to the word 1, 2, 3, 4. Now I'm imagining n equals 4 here. So apply that to 1, 2, 3, 4. S3 swaps what it sees in the last two positions. So we think of this as S1 of S2 of S1 of S3 of 1, 2, 3, 4. So S3 swaps the last things, the things in position 3 and 4, which happen to be letter 3 and happen to be letter 4. So we've got 1, 2, 4, 3. And then S1 swaps what it sees in positions 1 and 2, which happen to be letters 1 and 2. And then S2 swaps what it sees in positions 2 and 3, which is the 1 and the 4. So that's S1, 2, 4, 1, 3. And then S1 swaps what it sees in positions 1 and 2. So that's 4, 2, 1, 3. So the one-line notation of S1, S2, S1, S3 is 4, 2, 1, 3. The end.